So this phenomenon here, this cellular automaton, I said it was computationally universal, and it exhibits locality, and that's a very attractive property. In what sense is it local? Well, the information needed by a given cell as to what its fate is, whether it survives, whether it's colonized, it depends only on its neighbors, only on that very local information. There's no transfer of information that needs to take place over a long distance. It's just purely local. It's depending only on the things right around it. And that's very attractive in this world because wires take up space. There's limited bandwidth available to send things in optical or radio waves. And so if you can only depend on very local computations, it's very scalable. You could have the scale to a massive level, and there's no long distance interconnections that have to take place. The phone network has traditionally been extremely complex because there's long distance connections, long distance wires traditionally, which had to support it. In something like this, it's only very localized computation. And yet you could perform massive amounts of computation in parallel across the entire space. Concurrently, things can be evolving over here, over here, over here, and what's going on down here in the lower right doesn't have to wait for what's going on up here in the upper left. Do you see that? It's just going in lockstep. It can occur in parallel. Okay, so that's very attractive feature of a system like this. But we're not here to perform computations with it. Instead, we're here to try to see how certain assumptions about it make a difference. And I ended last week with certain assumptions. I changed the assumption here about these rules. I made it so it would survive, say, a cell will survive not if the number of cells adjacent to it is 2 or 3, but 2 to 4, 2 to 5. Does anyone remember what happened when I did that? Does anyone remember where this was encoded? Well, let's go to cell. Go to cell. And actually, if we scroll down in cell, you'll see there's this thing on before step and on step here. Now, this is very important, and it's something that I didn't emphasize last time, but I really need to. Because this sort of model, traditionally, this sort of cellular automaton is traditionally not only a discrete space cellular automaton, meaning it's divided up into chunks, discrete chunks, particular. It's not a continuous space. It's divided up into very specific sort of count of cells. In addition to that, it's discrete in terms of time, meaning time takes place in chunks, step by step by step by step. And here, there's instructions on what to do before a step and what to do on a step. On before step, each agent collects information that it will need based on the state of other agents. Based on the current state of agents around it, how many neighbors around it are alive. And then, on step, it then figures out, is it dead or alive the next time step, using this sort of logic here. And I argued that logic implemented those rules I said over there. So here, it determined if its cell was colonized. If it was colonized, alive. Currently, it's empty, so alive is false. So this whole thing is false, and it just cares about whether the number alive is around it that are alive is 3. By contrast, if it's currently alive, then it stays alive if the number around it is either 2 or 3. And this is fine for that because it's just testing if it's equal to 3. So either way, this implements that rule. Do you remember what happened when we changed that to 4 or 5? Does anyone remember? Did we get very similar dynamics? Anyone?
No, the screen was almost completely red.
Okay, good. So depending on the values, we had different things occurring. So here's for 4, for example. And notice it's settling into something that's almost stable. It's got these little wriggly things. But notice if we perturb it. Here, watch this. Watch my mouse. Ready? You could try this yourself, even at home. So you click you click around here, and it'll actually reconfigure itself a little bit. It will, and sometimes you can get it to actually trigger a big recomputation to a new stable state. I don't know if you saw that, but it just recomputed this. Essentially, I'm sort of forcing it into a situation where it needs a new state in order to be stable based on my orientation. So it's got a stable state here. This is with 4. And we saw similarly with other ones, if we did 5, it would go to it will have another pattern, etc. Okay. Now, let me ask this. I'm going to change this back to its original rule. Let me ask this. Why is it that you first here collect information on what cells are around you, and then you do the update? After all, why not collect information about which cells are alive around you while you're doing this step update? Why do we separate the two? This is a very important component of this discrete time consideration. Why do we separate the two? Anyone? That is it. John's bang on it. The idea here is we don't want the outcome of this simulation to depend on what order each cell is updated. If it did this computation right before updating each cell, when it's counting how many people around it are alive, some of those cells around it would have been updated already. Might have been updated already, and others not. And now we're kind of mixing what we're counting on. We're counting on some things as they were the last time step and some things as they are this time step, this coming time step. Does that make sense? So instead, we separate it cleanly out. We figure out all the information we need to do the update based on the situation before anyone updates. We figure out essentially all the information they're going to need about that situation. And then, when we go to update the cells, we just use that information collected just a moment ago before anyone updated. So it's not affected by whether the ones around it have updated it yet or not. Does that make sense? This is a very important point, and I'll emphasize this, because these sort of models can be very, very sensitive to what order different cells update in. If we didn't have this separation, it might depend a lot about, do you update the one in the upper left first, or the one in the middle first, and the one in the lower right, what the results were. By cleanly separating it, we get away from that issue. Does that make sense? Okay. So that's that separation of on before step and on step here. And it's a conceptually simple separation. Okay. So, ladies and gentlemen, what I'd like to do now is I would like to examine a different model. Okay? We may come back to this one. I may give you a little assignment about this one, depending if we have time to come back and explore it. But I'd like to go to example models right now, and I'd like to go to a model called the Schelling segregation model. Here we are. Schelling segregation, okay? And here we go. And in the Schelling segregation model, we're going to also have a cellular automata. So it'll be discrete space and discrete time, meaning it's divided up into chunks, rows and columns, and it evolves in steps, step by step by step by step. This is taking a while to load. So here, though, there's going to be a difference. Rather than each cell just depending on what's around it, we are instead going to have mobile agents. And these agents will live in these patches and move around. So there's going to be some patches that are empty and some patches that include agents, and those agents will move around freely. Okay? Sure. The model was called Schelling segregation, Schelling, Schelling segregation model. Do you have that? People have that? Okay. So let's go call up the Schelling segregation model. And what we're going to have here, ladies and gentlemen, is a grid, rows and columns. let's go look at the rules for a person. The rules for a person, the theory of personhood with respect to this model just includes, are they satisfied, and it assigns them a color, okay? Okay, now let's go select person, though, and go down to the same area of person that has on before step and on step, okay? So that's within within person, okay? Here, what I'd like to do, ladies and gentlemen, is I'd like to explore the implications of these rules, okay? So here we go. And we're going and taking a look at these features here. So, ladies and gentlemen, you'll notice there's the same separation of on before step and on step because we want discrete time. First, the agents figure out all the information they need to do their job, and then they do their job to make the step. Okay. So, can anyone help me unpack if this satisfied indicates if I'm satisfied? What are the rules here capturing? What is this on before step? What's kind of the rule captured in here? Under what conditions will I be satisfied? In other words, under what conditions after running this will satisfied be true? Anyone? No neighbors. Great, Wade. And
the count of the same color
is above, that's right, this fractional threshold of all my neighbors. So in other words, if my number of neighbors, if I have no neighbors at all, I'm satisfied. If I have a number of neighbors who are of my same color that exceeds or is equal to a fraction of my total neighbors given by threshold, so if threshold is 50%, I'll be satisfied if at least 50% of my neighbors are my same color. This loop here is basically totaling up the number that have my same color. That's what n same is. I did not create this variable name. Okay, n same. So it's counting up the numbers that are the same. Really, there should be is satisfied. Hear that? AnyLogic? It should be is satisfied. Yeah, we can do a lot better than this in terms of the software engineering of it. But basically, I'm satisfied if I have at least this threshold of people next to me who are my same color, or if I'm next to nobody. And now, in on step, what does this rule encode? What does this rule do? With probability, 30% probability. It's like I flip a biased coin. With 30% probability, if I'm not satisfied, I'll go somewhere else. I'll jump to a random cell, wherever it is. It could be in the middle of people like me or not like me, I'll jump to it. Does that make sense? Okay, now, this game was invented in the early 70s by a sociologist who was quite innocent of computers. He created this little game. He designed a little system where every cell would be occupied by a person of a single color. He used checkers, red and black checkers, and he put them on a checkerboard. And the cells were actually squares of that checkerboard. And either it was empty or it was red or black, according to the color of the checker. He actually thought he used checkers, red and black. It's conceivable he used pennies, head or tails. In any case, he had it on a checkerboard. And he was then playing this game forward, doing it manually, step by step by step, figuring out what its next step would be and then putting them in the appropriate places, figuring out putting them in the places manually. And he found that some interesting things could happen. What do you think will happen? From these simple rules, this is the rule for a particular agent. What do you think we'll see? Suppose our threshold is very low. Let's say 25%. What do you think we'll see? Anyone? Yeah.
Probably, even with the low threshold, segregation by color, which is, as a coming from sociology, probably a reference to color and racial segregation.
Okay.
It only takes a very low threshold as intolerance to lead to segregation.
Okay. So suppose the threshold is 0. What do you think will happen then, in that extreme case? No threshold. Then will I be satisfied or dissatisfied? Always satisfied. And therefore, will I move? No, I'll just stay there. And if we smatter people down at random places, it'll look totally random. Just as Ansgar said, as threshold rises, I'm getting more picky. I want to be with people who like me. Even 25%, I'd like at least 25% of the people around me to be of my color, and if they're not, I'll move. Then you might start to see some patterns. What if threshold is 75%? What do you think you'll see then? Very strong segregation. 100%? Sorry?
I ran them all
Okay. Okay, yeah, it's a lot better at computing it than we are. So let's run it. I like this. So let's go. So here we have these sort of lighter areas in pink. That's empty. We have red, and we have black. Okay. Now let's go here since it's. Let's go. If yours doesn't have the execution control, let's go down and pull down the time scale here so we could speed this thing up. And you'll notice that I sped it up, but nothing's going on here. This is 16%. Do you see any patterns? Let's start it over again. Just take a note at the initial pattern here. I just stepped it once. Let me do that again. Watch this. I just used this to step it once. So are there any big patterns here? It's just throwing people down in random ways. Any big patterns there? Okay, let's run it out here. So I'm going to set this thing down to, I'm going to set it to 25% here. I just drag this slider. Let's run it. Okay, I'm stepping it here. Yeah, it's moving. 25%. Do you see some patterns? A little bit, maybe. It seems to be some clustering that's going on. Red is a little bit removed from black. They're kind of bigger areas. Okay, now let's move it up to 50%. Okay, I just did 35%. Do you see a little bit more patterning there? Okay. Okay, now I'm moving up to something like, let's say 55% patterning. Yeah. Okay. I'm going to put it at 50% here, but there's a little bit of an issue here because if you have it higher earlier, and then you go back to a lower color, it's satisfied with that, right? If you demanded a higher fraction of people around you be like you, and then you relax it to be a lower, you're gonna. As long as it was stable, you're going to stay in the same area, okay? So suppose I move it to 71%. Suppose I move it to 80%, 81%. Well, just as it was said, you get these broad patterns for a while. Okay, now what's going on there? Anyone? What's going on at that really high rate? Yeah, that's good. There's no way they can all be satisfied at the same time, right? And so they're all constantly moving around, searching trying to find some satisfaction, but they can't get it, right? So here we have a situation where it's very, very entropic. By contrast, there is a point. There's a point where there's a phase change. If you lower it from that very high level to something like 75%, you can get something like that. There's a phase change going on here, going from 75% to something higher. It becomes untenable, impossible, and you don't really get much segregation at all. But at 75%, you have this very pronounced kind of larger scale structures. These are emergent patterns, just as much as those waves of infection we saw that first day. Also, incidentally, a cellular automaton, although in continuous time. And here we have these people sorting, each person only depending on their local situation, each hopping in a myopic way without knowing whether the place it's hopping to is any better. But it forms these big patterns. It forms these pronounced high-level features that are much more ordered than either this or, indeed, than something when we have only a low fraction, when we have only a low threshold here. So ladies and gentlemen, we have here a cellular automaton which exhibits emergence. And this is a very eye-opening model. For sociologists, this was of considerable interest. And it suggested that to get large-scale patterns of significant segregation, like something like this, at 25%, you don't need to account for all sorts of very involved mechanisms. Even slight preferences on the part of individuals, such as that, a quarter of the people around them look kind of like them, can lead to significant patterns associated with segregation. There can be significant issues in terms of the sorting that emerges. And you don't have to appeal to explain this level of segregation. You don't have to appeal to residential steering and predatory bank practices and out-and-out overt hostile type of actions. It can be slight preferences in terms of sorting. And in that sense, the model is very insightful for people. It opens some eyes that, wait a minute, these very simple rules, if you just put them together consistently, they can actually explain some patterns which otherwise might be thought to require very sophisticated theories. Now, does this prove that, all similar levels of segregation in the world are purely resulting from this? No, it doesn't. But it leaves open, it helps us think through and get insights about what a simple theory could explain, and therefore helps us in scientific investigation of phenomena like this. This is segregation patterns emerging from just individual preferences in sorting, emerging. And indeed, I know some people who have spent much of their academic lives working on probes using real urban data of patterns like this, trying to understand how people's actual decision-making patterns might yield overall patterns like this. You notice my emphasis on emergence here. We have these individuals who have very simple rules. Simple rule about moving, if a certain fraction of the people around them are not like them, probabilistically moving. And from it, we get these very big high-level patterns that we can't reduce to any one person. It's not like we can immediately see these patterns coming from that rule. But they emerge from them together with the structure of the space, etc. Okay, so that's good. And we could play around with this model some more. For example, you could make it more likely that a person moves or less likely. You could make it so they only jump to areas where people around them are more like them. You could make it so they don't tend to jump nearly if they've jumped recently, etc. And I could, I'd welcome you to do that. But today I want to challenge us to implement this model a little bit differently, and to try implementing that other model associated with the game of life differently. Okay, so ladies and gentlemen, I would like you here to create a new model, okay? And we're going to build up some similar models. So, new model. And this model will be called game of life. And it will be called continuous time. Okay? And I'll put in my normal game of life continuous time. So rather than having all the agents move in lockstep, we're going to have them move instead in a way that's going to be based on sort of a certain probability per unit time, a hazard. Rather than having everyone update at exactly the same time, it's going to be asynchronous. Some agents may update slightly before others. We're not going to need to update all agents at a time. Very important point about discrete time updates. If you have everyone update at the same time, there's this awkward question, well, who updates first? And this need to kind of save away information. Is there not? You see what I mean? If you update everyone at the same time, unless you're careful about squirreling away all the information you need to make your update, you may be in a situation where now your update depends on whether someone around you updated, so it requires you to kind of do extra work, pack up all this information for you to use. By contrast, continuous time just allows different people to update at each their own time, and we don't have to worry that everyone around them is also updating and therefore to capture the information. Okay, so ladies and gentlemen, with this new model, we're going to implement this game of life continuous time. Okay? So in the first step, I would like you I'm going to ask you, what do you think the agents will be in this model? What do you think the agents will be? Given those rules over there, which we'll capture, what do you think the rules, how do you think we're going to build this model? What would the agents be? Cells? Okay, you're a good idea here. That's one way to do it. You could do it with cells. What's another thing we can make an agent? How about make an agent be the patch? Remember, in Schelling segregation, the agents have to move around. In game of life, do they move? Is an agent moving somewhere else? Are they hopping? No. They're just, either the cell is living or dead, right? Or either the patch is living or dead. So I'm going to suggest here that to make it simpler, because we don't need agents to move around and so on, we're not going to have cells that can ooze around. We're going to instead have an agent be the patch. Okay, it's going to be sort of a patch-centric model. Okay, now, ladies and gentlemen, we're going to go through the discrete environment here. So I would like to lend this patch something a little bit more. I'd like to lend it a rectangle up here. So for the patch, I'd like to create a little rectangle for it. The initial color of this rectangle will be black. And the rectangle, ladies and gentlemen, will be of height and width 3. Okay? How did I do that? I selected that rectangle, and I went and I set its height and its width to be 3 in the position and size. So it's going to be a really small rectangle. Is that okay? Okay. Okay, so that is a good start. Okay. The next thing I'd like you to do is I'd like you to go to main, and in main, ladies and gentlemen, I'd like you to scroll down to the area in main that has to do with the space in networks. And I'd like you to set the columns to be 200 and the width and the height to be 600. So let's go do that together here. Okay. So in main, I'd like to scroll down to that place where you say space and networks. And we're going to set it, very importantly, to be discrete space and networks. It's divided into rows and columns. It's not, you could be at any space, 52.3, 62.85. Instead, it's going to be discrete, okay? And then we're going to want to set these values here, okay? Now, it's exhibiting truculence for me, so pardon me as I, okay, so what's going on here? Okay, autosave failed. Okay, this is a most unexpected circumstance. I don't think so. It shouldn't require that. Okay, it says autosave failed. Let me save this. Okay. Okay. Well, this is absolutely fascinating. So please set it to be 200 rows, 200 columns, and 600 across. Okay. I'm going to close this and I'm going to reopen it. Here we go. Reopen it. There we go. Does anyone else have that problem, or it doesn't? Oh my goodness. Okay, so it's not just. Oh, is that right? Oh, okay, wonderful. Let's drag patchen. Thanks. I learned something from my students every day. That's great. Great. So let's call it patches. Okay. Let's make it a population of agents. How many agents will there be? 200 by 200 of them. Okay. 16,000 in short. But make it 200 by 200. Why does it make a difference? Why am I so insistent on that? Make it 200 by 200. Anyone? Yeah, it's easier to add. It's explicit. It makes it very clear what it means. Sort of where it's coming from. It makes it more transparent. Okay. So game of life. Okay, sorry, I'm in the wrong one here. Here we go. Okay, so 200 by 200. That's good. And let's compile it, make sure it's a happy camper. And then let's scroll down to that network area, okay, of main. Okay, great. So if you go down to network, now we can change it to 200 by 200, rows and columns. And we're going to have the width and the height be 600 by 600, right? Does that make sense? Are you okay with that? Speak on. Yeah? Okay. Okay, and now, this is very important. More 8 neighbors. What does that mean? Yeah. So when we consider the neighbors for a given agent, we'll count the ones all around it, not just north, south, east, west, but northwest, northeast, southwest, southeast, right, as well. Now, the layout type, this is very important. The layout type is going to be arranged. Okay? That's still in that area, space and networks, but it's going to be arranged. And it's going to apply it on startup. Okay, what do you think we should see now if we run this? What will we see? What lies before me? And why is it black? Yeah, because at each cell, at each row, each grid square, there is a patch, right? Does that make sense? Okay, great. So we have these patches now. They're laid out, and you should see that. Now, Alan sits ready to help. Okay, sector 1. Okay, okay, who else needs help? Okay, we have a rapid deployment force in the wings if we need it. Okay, this is great. So, ladies and gentlemen, next step is we're going to lend us some dynamics, okay? So there's going to be in the patch, what do you think we need to characterize in the patch? This is a patch. What do we need? What are the possible, remember that description I had for an agent-based model? You have parameters. For agents, typically, you have state. You have actions that change state. You have rules that modify those actions. And you have time, and you have environment here, right? Environment. Okay, here, our parameters will go pretty light, actually. But what state do we have to maintain for each patch? Yeah, is it live or dead? So let's call it living and empty. Okay. So let's go to palette. You can call it as you see fit. I'm going to call it living and empty. So I'm going to go down to the state chart palette, and I'm going to drag this in with a state chart, and this will be called occupation state, something like that. And so it's going to be living, or it's going to be empty. Okay? Empty. Okay. That's great. And I'm going to have transitions between them. Okay? Great. And initially, these transitions are going to be I'm just going to leave them as timeouts. We're actually going to make them a little bit more complex in just a minute. Okay? So it's going to look like something like this. Now, what else do we need? Well, we need some visual indication, right? Whether it's empty or live. Okay? So, ladies and gentlemen, what I would suggest is that we do so with a color. So how are we going to denote the color? How are we going to implement that? A variable. Yeah, let's go add a variable. It's not the only way. With it being dichotomous, just two of them, we could actually do it with a nice little sweet rule in there. But let's call it color, the variables of type other and color, and its initial value will be black. And then, upon entry to the living state, its value will be green. Right? Color equals green. And then in the entry to the empty state, its value will be white. Something like that. Okay. Then we'll know if it has been initialized because black is another. Now, what else do we still have to do in order to complete the thought? Anyone? What do we still have to do? It's just having this variable called color. Does it do it automatically? What do we still have to do? Set the rectangle to have that color. So in the rectangle, at the fill color, let's set it to have color. Okay? Great. Yes. Absolutely. Okay. So thank you. I was going to do that and think about this recap. And that's great. Much appreciated, Alan. Okay. So what did I do? I added in a flurry here. I added a bunch of features. Okay. First, I added a thing called occupation. Oh, this should be called occupation state chart, not state. I stand corrected. Occupation state chart. Okay. Then I added two states and transitions between them. The transitions I just left at their default values. And I further added a variable called color, type, other, color here, initial value black. And for living, I set its color to be green. For empty, I set its color to be white for that variable. And I didn't futz with the transitions. Those are just temporary things. And then up here in the little rectangle, I set its fill color to be black by clicking on this thing so that it's dynamic and putting color. Are people okay with that? What should happen right now if we run it? What do you think will happen? What will we see? Oops. Oops. Okay, it's unhappy. Okay, let's go figure out its happiness. Okay. Oh, did I say empty? Oh man, sorry. Color equals white. Okay, core. Color. Core. Okay. Okay, what will we see? What will present itself? That's interesting. So basically, it's just updating the color, just going back and forth between white and green with a mesh of sort of over it. Okay, so that's fine. That's fine. With this, it brought out the fact that our rectangle has little lines on it. So if we go back to the rectangle, we don't need. You'll notice there's a line color black, and we'll set it to be no color for the line color, and that will mean it won't have this kind of mesh around it. So I went back to this rectangle and I set the line color to be no color. And so here we go. And then it's going back and forth. You see that? Okay. So we got the basic mechanism set up. Okay, now we need to do the heavy lifting. Wow, what a great model. What a great model. Okay, but this is very limited amount have to do with the game of life yet. Okay, now let's get down to brass tacks. We've got all the infrastructure in place. What do we got to do? And how are we going to do it? Okay, so you tell me, under what conditions will a cell go from living to empty? Under what conditions will it go from living to empty? Sorry? Good. Okay. So what I'm hearing is it's contingent. It's not just every time step it's going to do it. Instead, it depends. It depends on what its neighbors are. So let's go down to the state chart and make a conditional transition, right? Here we go. Just like that. Okay, and then, ladies and gentlemen, does it always go from living to empty? No, it's conditional. So we need something going back here. By default, it'll stay living. Under a certain condition, it will go and die. Okay. Now, actually, I'm going to take this back because people are bad about dealing. I'm talking people in general have trouble reasoning about double negatives. So I'm going to make the default actually becoming empty, and I am going to make the condition be staying living. Okay. Now, under what condition will it stay living? Under what condition? Good. Okay. So, ladies and gentlemen, we have our choice to implement this in several different ways. We could have a thing along here which counts up the number around it that are live, figures out how many there are, and applies it. But we need similar infrastructure to go between empty and living, because after all, that depends on what? This transition over here between empty and living, what does that depend on? What does that depend? Same sort of thing, the number of people. So let's not hard code that at two places. That, ladies and gentlemen, is fragile. And taken on a large scale of software engineering, if you go and you paste in code here, as Shakespeare said in King Lear, that way lies madness. Mark my words. Cut and paste is hazardous to your mental health. Okay, so on a large scale at least. Okay, so ladies and gentlemen, let's go create something that dignifies that. Let's go create something that computes. It's a function, and it computes the count around us. Okay. So it's going to be called count living neighbors. And yes, we can spell it in a properly Canadian way. Okay? Okay, good. Count living neighbors. And count living neighbors, what sort of thing will it return? No, it's actually an int, because we're going to use it in two different places. Sometimes, you know, whether or not we die is going to be different things. So, okay, so count living neighbors can return an int, as suggested by its name. Good name will often connote what does it return. Okay, or does it return? If it doesn't return anything, you could say perform this, compute, or actually not compute, but perform this, do this. Okay, so what is it going to do? It's going to count up the number around it that are at same neighbor. Okay, great. So let's go do that. Int count living neighbors equals 0. Great. And then for each neighbor, if its neighbor is living, we're going to increment it, right? So for agent neighbor, okay, actually we need to, well, okay, we could get the neighbors every time, but that's going to be a little bit awkward. We could do it, but what would be sweeter is if we just compute our neighbors once. After all, they're not going to be changing, the patches that are our neighbors. True or not? Remember, this is a patch. It's not, the environment around it is not changing all the time in terms of which patches are around it. What's changing is whether those patches themselves or not. But the actual patches around it are fine. So, ladies and gentlemen, let's create a variable called neighbors. 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 Okay, great. And ladies and gentlemen, this variable will be of type other, and with some regret, I will declare this to be an agent array, an array of agents. You'll see my reasons for my madness in a moment. Okay? An array of agents. Other agent, begin bracket, end bracket. Okay, who needs Alan's help? Okay? Okay, now, count living neighbors then. What is it going to do? It's going to loop through those neighbors for each agent in, so I could call it for each neighbor agent in neighbors. It is going to do what? Well, it's going to need to tell, are they in a given state, right? Are they in a given state? Okay, so, ladies and gentlemen, one thing you could do is you could do it this way. If neighbor, I should call it, sorry, neighbor with a U. I fall back to my patterns. Okay, if neighbor agent dot in state, if it's in, which state do we count upwards? If it's in the living state, okay, good, at least someone's listening. Okay, then we increment count living neighbors. Right? Okay, great. And then what do we return? Count living neighbors. Okay, great. That's it. We're done there. Okay. Great. Now, that's good. So, ladies and gentlemen, let's build this model and see if it's a happy camper. Count living neighbors. Remember, it returns an int. And this is the code here. Does anyone want me to put this on a big screen? That code. All we're doing is we're getting a variable that counts the number of neighbors. We're looping through each neighbor, and we're seeing, oh, okay, Now, is there a possibility that someone will have no neighbors at all? That wanted it blown up? Okay, you got it. Notepad. Okay, notepad. Boom, boom. Here we go. Okay, there we are. For each neighbor, we check if that neighbor is in the living state, and if so, we count them, otherwise not, and then we return the count. There should really be a space here to get the nice visual flow. Okay? A new line to me. Are we okay with that? Okay. Clear enough. Could it be done a little bit nicer with Java 8 functional constructs? Yeah, a little bit. A little bit. It would be sweet. But I'm going to leave that out for now. Okay, great. Count living neighbors. Okay, ladies and gentlemen. So, having computed that, let's now suppose that we want to encode the condition under which this person goes back to living. How do we do that?
Count living neighbors return 2 or count living neighbors return 2.
Okay, good, good. So we could write that out. We'd be calling count living neighbor twice, which is a little bit wasteful. And we'd like this model to go pretty fast. We're going to have a lot of agents in it. So I'm going to have a function. I'm going to add one more function here that says is remains alive. Now that sounds really kind of awkward. So maybe I'll just say remains alive. In some languages like Scheme, you can actually have a question mark as part of the name, in which case it connotes it returns a Boolean. In Java, we normally say is or has, but is remains alive sounds a bit will remain alive. Yeah, is habitable. Is still alive. Is surviving. Okay, is habitable. I don't know. I kind of like is habitable. How do you like that? I know you hate it. Someone kill it. Is habitable. Is inhabitable. Is at least it works with is. Okay. Okay. So I'm going to call it now. Secretly, you folks can call it whatever you want. I'm not going to go around. Alan's not going to police that. Get your binoculars out, Alan. Okay. 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 So it returns what sort of thing? Boolean, right? And here we're going to go create a variable int count neighbors, and we're going to count we're going to count neighbors, and we're going to call count living neighbors. So we're going to first get the value of that function, and then we're going to return is count neighbors greater than or equal to 2, and count neighbors, the variable, less than or equal to 3. So for those who want to see that, that's what I did. So all I did is I avoided counting it twice, going through this dumb thing of calling it 2 times. Are there other ways that could have avoided that? Yeah. This didn't seem too bad. It can have a name at least the instructor feels is nice. Okay? Are we okay with that? Oh, thank you. Okay. Yeah, Ellen knows my tendencies. Okay. There we go. Thank you. Okay, let's I should have made sure it was a happy camper. Okay. Are people okay? Ready to go on? Okay? Okay, ladies and gentlemen, now let's complete the reverse transition. How do we do the reverse transition? What do we need going the other way? What sort of thing do we need there? Okay, good. Good. We need a branch. Good. Excellent. Okay. There we go. Boom. And then we have this transition here and have it go up to here. Great. Okay. And yes.
Why can I not just go to the branch?
Sorry. What?
It happens the same, right? So why don't you just go to the branch?
Go to branch. This is.
Just to the branch we have already. I mean, we want to do the same, right?
No, because this one. That's a very good question. But this one is, if this is empty, it's going to only be occupied if what? If there's exactly one cell next to it, right? So this one here has this condition. It's a very good question there. Oh, you know what? We haven't put the logic in for this, so it's not obvious. Okay, so folks, for this living one, we forgot to put in actually the logic. What is this one going to say? Is habitable, right? And I think the question that was asked here is a very good one. Well, the rule here is actually tighter for this one. It needs exactly 3.
Okay, then
Yeah. This is habitable. This one here, under what condition will this go on to living? Anyone? Here? Under what condition will it go on to living? Anyone? Yeah, count living neighbors exactly equals 3. Now I could create a function for it, and that would be my natural inclination is colonized, but if colonizable, but let's leave that for now. Okay, great. So, ladies and gentlemen, let's rehearse this again. We have this transition going every 1 time unit. By default, it goes into here. If it goes into empty, it's only if it is habitable that it goes back to living. This one also goes off after 1. By default, it stays empty. Under the very special condition that count living neighbors equals 3, it continues on. I'd like to label those transitions, but time is a-ticking, so I'll leave that to you. Okay, so ladies and gentlemen, are you ready to try this? Are you ready to try it? Who needs more time? Would you like me to show something? Would you like me to show you one of these items in the model? Okay. Okay, you want to run it? Okay. What do you think will happen? Anyone? Oh. Oh, great. Okay. Thank you. We didn't initialize the neighbors. Thank you. Okay, so let's initialize the neighbors in the entry here. Thank you. Neighbors equals get neighbors. Unfortunately, the latter is spelled according to the dictates of the American Imperium. Okay, so there we go. Neighbors equals get neighbors. And for those whose language native is for whom English is the second language, I apologize. I'm mixing. This one sentence mixes 2 different spelling systems. Okay, great. Are we ready to go? Shall we run it? Well, we haven't really done everything yet. We actually still have all agents starting living, right? And that's going to lead to pretty boring behavior. So let's make some agents start living and some dying. How are we going to do that? Anyone? How are we going to split them up? So some start living, some start empty. A branch. go put a branch there. Okay, here we have a branch. And let's go put a transition here. And then let's go put a transition here. Okay, and let's go put a parameter in main that's called fraction occupied. Okay? Fraction occupied in main. It's a parameter. It's some assumption we're going to make in main. It's going to be called fraction occupied. Fraction initially occupied. Okay? And it's going to be a double, and by default, it's going to be 0.1. Okay? 0.1. This is in main. And now, in patch, for the condition, let's make the default be empty. And under what condition will it go to living? Anyone? Under what condition will it go to living? Random true. And based on what random true thing? Fraction occupied, initially occupied. So with that probability, it'll end up in living. Are people okay with that? Who needs something shown more carefully?
Where did you initialize the neighbor's value?
I put it, great question. I put it in here, John. In the entry point, I set neighbors equals get neighbors. It's this logic, and it's in the entry to the state. It's in the entry to the state chart right here. I just assigned it. Okay. Who needs me to show something? Who needs? Okay. What would you like?
Just before, or just after you added in the branch from the entry point.
Yeah.
Back to the main.
I did. I went back to main and I added fraction initially occupied. I made it a double with initial value 0.1. Yeah. And then in the patch, I made this branch. The default went to empty, and this one had a condition, going to living, had a condition of this. Okay? Okay? Who else would like me to show something? Okay? Yes. Uh-huh. Okay, so condition of this guy here, it's this. Yeah. This is the new parameter in main that I added. Whose default value is 0.1. And this is the condition under which it goes here. Okay? Who else would like help? Okay, yeah? Okay, good. Great. So this guy here is just a timeout, a standard timeout. It didn't change it at all. This transition from this branch to here is a condition going up here, and the condition is this. So it's testing if the number of neighbors is exactly equal to 3. Okay, other questions? And this default one, Dana, is just the default. Okay, who else has questions? These are great questions. Yes?
That specific has to be 1. I get an error message saying that the left-hand side of the assignment must be a variable.
For which?
For the transition you just described.
Oh, for this guy, it needs equals equals?
Oh, sorry.
Sorry, we live according to the dictates of the Java Imperium. Okay? Okay. So this is equal equals? Yeah, it's testing equality. It's not assigning. Yeah. Okay. Anyone else? Are we ready to run? Okay. Maybe some of you are already running it. What do we see? What do we expect to see? This is totally deterministic right now. What's going on? What's going on there? Yeah, so here we have no randomness. What we're not doing is we're not doing this very careful step of figuring out, of making sure that each agent updates independently of all the agents around it. So whichever agent goes sort of first here, we allowed to go first. We didn't separate that out, and we get that logic. Now let's change this, ladies and gentlemen. Let's change this from a timeout to actually have some stochastics. Let's make it a rate with an average time of 1, in which case we just leave it as 1 per second. And let's make this guy a rate. So just on average, they'll be sort of checking how many cells are on them. What do you think the results of that would be? Now we have stochastics. What do you think will happen? Well, you see actually quite similar behavior to what we did just a moment ago. The amazing thing is, let's emphasize this, folks. I want to bring home this point. Just a moment ago, we saw even when it was totally deterministic, because there was some coupling of which one got updated first, even though it's totally deterministic, we saw a pattern emerging, a very regular pattern, very different than what we saw in the original game of life. And now what we just added, what I just did was I turned these to rate transitions. So they're going off at a certain rate. And now take a look at this. We actually have something which is quite ordered coming out of randomness. This is actually quite a bit more ordered than the original game of life, isn't it? I mean, there's a lot more sort of vertical lines and horizontal lines, and I can kind of go futz here. Well, okay. Well, we'll do that in a second. And we have a lot more order than in the original game of life here, at least a lot more overt order. But we have more randomness, too. So it's not always you add randomness and it makes it more disordered. There's actually a fairly complex coupling going on here among sort of what's going on in terms of how these rules interact, which defies easy understanding. Okay, ladies and gentlemen, let's complete the exercise by doing the following. And we're in the final minutes here, so we'll have to move quick. I'd like you to go to Patch, and I'd like you to go select the patch. If you have trouble doing that, you could zoom in and select it, and you could do so with this, or over here in presentation, you can select the rectangle here, okay? Now, I'd like you to scroll down, and you'll notice that down in the advanced area, there's an on click, okay? And basically, I want to toggle this, okay? So there's several ways I could do it. I'm going to just do it this way. I'm going to say this.send toggle. So I'll put it up on the big screen here. This is what I'm doing. Oh, what am I doing? This is what I'm doing. This.send, oh wait, sorry, I need another this. I am sending the message to myself that says this. And so there's two thises. One is who sent it, so don't ignore it. Okay, here we go. Come on, get back there. Okay, there we go. Boom. This is what I'm doing. I am sending a message to myself that says toggle. Okay, now how am I going to enforce the toggle? How am I going to get it to switch states if I get a toggle message? Anyone? Yeah, let's put in some transitions. Oh, this is horrible. Okay, that looks like. Okay, let's go back. Okay, okay. Well, you could prettify it a bit. Okay, so ladies and gentlemen, let's go put on two transitions. One to go one way, one to go the other way. What sort of transitions will they be? They'll be message transitions, okay? Great. And this will be based on receipt of a message, and it will be unconditional. It doesn't just matter what message it is, as long as that's in that state, we will get it. Okay, just about done here. We're in our closing minute here, and let's change this to be a message transition. Okay, so what this means is now when we double click on an agent, we will, so all I did is I dragged these in to this, I reorganized to give myself some space, I drag these in, make them a message transition and an unconditional message transition. Okay, ladies and gentlemen, so if I run this now, I can go, you notice I can like disturb things that are already organized by running this out more. You know, the hegemony begins. It's spreading. And I can perturb the nature of this by clicking around here. And you'll notice that small perturbations will in fact lead this to get sort of altered. I can also go modify things up in this area. Okay, notice that there are stable entities, even though they're stochastics here. Stochastic as to who updates first and so on. There are stable entities. When we started it, it quickly shakes out to have stable entities. These are stable things. No matter who updates first, they will be stable. Do you see that? And those stable quantities, despite the randomness, they're persistent, but they get swallowed up by this kind of overall structure that emerges from the rules. Yes, Ansgar.
So the name of the model is continuous time, as if that was differentiating it from the previous model. But how is the rate space?
Right.
How is that different from the steps that we take in the previous model?
The steps in the previous models, I didn't show that, but those steps are at fixed times. These rates are going off with a certain chance per unit time, and they can occur at any time during that interval. They might occur sooner during that interval or later during that interval. Remember, the residence time is exponentially distributed. Remember that? Your chance of leaving during a given sort of time step declines like this. And so a lot may be leaving soon, some may be leaving later. It's continuous time. And that's what we have going on here. And yet we still get, despite that randomness as to when people leave, we still get this more order than we had in the original game of life. That's the amazing thing. Adding randomness has actually supported more order here than the original lockstep rule. Even though the lockstep rule is very ordered in a way, everyone updates at once. It did not lead to more order there than you have here. This is actually quite ordered. Does that make sense? Yeah. Okay, so we've seen this. This is a stylized model. It's a model where very simple rules lead to some quite complex global patterns. And we've seen that it's very sensitive, very, very sensitive to particulars, whether there's continuous versus discrete time, which agents update first, what the exact rule is in terms of survival, whether it's between 2 and 3 or 2 and 4, or 2 or 5, can make a really big difference in non-obvious ways. The emergence is complex, and it results from extremely simple rules. And this has inspired actually some physicists to go out and look. This sort of scenario has inspired some physicists to go out and look for sort of extremely simple rules that might, when put together in a consistent way, explain a lot of different phenomena through extreme simplicity. Things that we think of as requiring totally separate explanations may have a common, extraordinarily simple set of rules that give rise to them. I won't take an opinion on that, but what I will say is that simple stylized models help us realize the very complex consequences of simple assumptions in ways that are sometimes very useful. And whether it's the Schelling segregation model or this one, we can get a lot of insight by building up models that don't necessarily always reflect lots of texture in the world, but just very simple assumptions and seeing what the outcomes are. I would put as a challenge to you whether you could create a similar model, maybe based around this one, for the Schelling segregation. Try to do something similar for Schelling segregation, and you'll actually find that you could perhaps create it with not just two types of agents, but multiple types of agents and see them update over time. Okay, so that's all I have time for today.